transformations of rational functions. In previous courses, you learned how to draw the graph of the reciprocal of a function. For example, when given the graph of y equals 2x plus 3, you learned how to draw the graph of y equals 1 over 2x plus 3. The function y equals 1 over 2x plus 3 is an example of a rational function. Okay? So in 20-1, when you were doing that, how do I draw the graph? Where there were like 5 steps, which I think we went over really in the first day or so of the course. Right? So what do you need to learn? And that was in there, the remember how to draw a rational. Okay, well, we're going to go over it again now. So a rational number is a number that can be expressed as a fraction a over b. Rational number, where a and b are both integers and b is not 0. A rational function is a function that can be expressed in the form p of x over q of x, where p and q are both polynomial functions, and q of x is not 0. You can't do that, right? You can't divide by 0. Examples of rational functions are, so y equals 1 over x, rational function. You can even put really y equals 1/2. You know, these are still polynomials, but we don't generally think of it that way. F of x is negative 5x plus 3 over x plus 2. G of x is x squared minus 4 over 3x squared, etc. Right? So just two functions, one written over the other, and the denominator cannot be 0. Right? That leads to restrictions we got to be aware of, right? The basic rational. So everything starts as a basic, right? In 20-1, it was this basic quadratic, and then we did stuff to it, right? But we knew what the basic quadratic looked like, so we have to get an idea, what does a basic rational function look like? And we're going to do that with 1 over x and 1 over x squared. So the partial graphs of y equals x and y equals x squared are shown. Accurately sketch the graph of 1 over x and 1 over x squared. So we're just going to basically use the methodology that we used in 20-1 of how to sketch a rational function. So, does anybody remember? No, seriously. Yeah, what are we looking for?
Start with invariant points.
Start with invariant points. So where do I find the invariant points? Y equals 1 and y equals negative 1. Not 0, there's something special at 0. So we go along the line y equals 1 and we say, you're an invariant point. And we go along here and say, you're an invariant point. What happens when y is 0 on the original function? Because we're going to end up with 1 over 0. So what do we end up with? We end up with an asymptote line. So when the original function is 0, we get an asymptote line. Okay, so we sketch that in. Then, okay, I've got the invariant points, I've got the asymptote line. So now I just sort of ask myself, as these x values start getting larger, 2, 3, 4, 6, and I want 1 over, so 1 over 2 is a half. 1 over 3 is a third. And then we got a quarter. And then, so what happens with these guys? They start getting smaller. Do they ever reach 0? No. Because you're always going to have 1 over something. Even when you're out at 100 billion, you've got 1 over 100 billion, which is small, but it's not 0. Okay, so here, this goes down like so, which means, what is this line then here?
Sorry?
What's the positive x-axis? It's also an asymptote line, right? Because the curve is going to approach, but not touch. So we can go out here and say, all right, got an asymptote going out there. Now, what happens as the x values get smaller? So let's say when x is 1/2, what's 1 over a half?
2.
2. 1/10. What's 1 over a 10th? Let's just go with 10 and make it 2. What's 1 over 1 millionth? 1 million. So these values get really high, but will they ever get to be, well, you can't do 1 over 0, right? So we can get close to 0. You get like a millionth, And that would give me 1 million. So these values just sort of climb and approach the asymptote line. All right, what happens on the other side? Same thing, but in a negative fashion, right? So these guys becomes 1 over negative 2, which is negative a half, and so on. So these become small. And what kind of line? So now this is still an asymptote line, right? So this whole horizontal line, also known as the x-axis or the line y equals 0, is an asymptote line. And then what happens here? Going down, right? Same thing. So as we've got small numbers. 1 over a very small number is a very large number. These are small negative numbers, so we get large negative numbers. So that's your basic rational function, right? You look at something, it's that shape, you say, hey, that's a rational. And you do x squared then, right? So same method. I'm going to... Okay, so you're running through this. So you go along one, you say invariant point, invariant point. Say values are getting bigger, so values are getting smaller. You say values are getting smaller, so values are getting bigger. You say values are getting bigger but positive, so values are getting smaller but still positive. And values are getting smaller but positive, and so we've got that. And then we've got 0 here, so there must be an asymptote line here. And these guys are going down, but never reaching this line. So we've got an asymptote line here. So that's y equals 1 over x squared. So now we just want to list some of the properties of these things. So what's the non-permissible value of x? Okay, so non-permissible value of x is that x equals 0. If we do that as a restriction, what would the restriction be? No. X cannot equal 0. So the non-permissible value, we say x equals 0. It's almost a way of saying, what's the equation of the asymptote? If it's a non-permissible value, what's the equation of the asymptote? It's x equals 0. If you're doing domain, it's x cannot equal 0, right? I can have any x value I want except 0. What's the equation of the vertical asymptote? X equals 0. I'm going to say non-permissible value. That ends up being the equation of the asymptote. What's the equation of the horizontal asymptote? Okay, y equals 0. What's the domain? And how do we want to express it? So in set notation, what would we say? Set of x such that x cannot equal 0. In interval notation, you would go negative infinity to 0, 0 to infinity, round parentheses all around, saying basically we're excluding that value. What's the range? Set of all y. Whoops. What's below that? The end behavior. As the absolute value of x gets large. So that's as x gets to be positive and really large, then what happens to y? So y does what? It shrinks, it approaches 0. And by absolute value, we handle that whether it's a large positive x or a large negative x, right? We're just saying as the absolute value. As the value of x gets bigger, whether it be positive or negative, then y approaches 0. Behavior of the graph near the non-permissible value. As x approaches, let's just go look at the graph. So as the x values approach the non-permissible values, then what happens to the y value? It gets really large, going to infinity or negative infinity. Okay? So it approaches infinity as the values get very large, so it approaches positive infinity or negative infinity. So we would say the absolute value of y, it approaches positive infinity from one direction, negative from the other. So the absolute value just approaches infinity. So approaches infinity. Okay, so now you try that for the right-hand side. Bless you. Do everything in pencil just in case, right? There's a lot of similarities. There's a couple of differences, right? So, non-permissible value of x. Write in the restriction as well. There's going to be a change here. So, what's the difference? What was actually pretty much the only difference? Well, there's two differences. So, what's the first difference? The range. So, because you're squaring it, it's now going to become positive, right? So that we don't have, so then it's just y must be greater than 0. Over here, it's y cannot equal 0, but you will cover the negatives. You square it, then there's no negatives for the y value. Here, it is approaching infinity, either positive or negative infinity, and here it's only approaching positive infinity. Okay? And we're going to run into these scenarios, when we do calculus, and we're looking at, so you've got graphs. They do this, or they do this. And it's like, how do we tell? And we're going to have to examine it and say, does it approach positive infinity or negative infinity? I need to know that if I want to graph it out, right? If I want to be able to draw this. Okay? Questions on this? If it was a downward-facing parabola, if it was a parabola, then the range is infinity. There's no approaches, right? Approaches infinity is on an asymptote. As you're coming down asymptote, you approach it goes to infinity. The graph of y equals 1 over x is transformed to the graph of y. So again, transformations, right? But x minus 4 only ever does one thing, right? 4. That minus 3 on the end only does one thing. Down, I couldn't say right. Down 3. And that 2 only does one thing, but it's a little obscure at the moment as to what that 2 might be. So we may want to just rewrite this into a form where we can look at it and read off the transformations. So, describe the transformations in the correct order that were made to the graph of y equals 1 over x. So a couple ways you could do this. You could start with y equals 1 over x and then say, well, that 2 has something to do with it. So I could make it y equals 2 over x and say that's a vertical stretch by a factor of 2. Or we can take this and just kind of back it out a bit and say, well, what if we write it as y plus 3 divided by 2 will equal 1 over x minus 4. So I add 3 to both sides, but I want to get rid of that 2, so I'm going to divide both sides by 2, because I started at 1 over x. Okay, and now I think we can look at that and say, oh, okay, I see what the transformations are, right? So the first thing that happened was what? Vertical stretch by a factor of 2. And if you like, you could say about the x-axis, but we're stretch certified. So. Any other stretches? Because we got to go in order, right? Okay, stretches. Okay, any reflections? Okay, you see a negative. No, the only negative I see is x minus 4. I don't see a negative. So no reflection. Okay, then what? HT, right 4. VT, down 3. Okay. You can get that. You can get that off of here, really, right? You could say, you multiply that by 2, right? Because it started out as 1 over x. Now there's a 2 over something. X minus 4, I know what that is. Now I got a 2 over it. Okay, then it must have been a stretch. Okay, and then this, and then this. Okay? So how you do it? Another way, of course, you could start off as y equals 1 over x, then write it as 2 over x. Or write it as y over half equals 1 over x, and then at some point I'm going to drop doing a lot of that and just throw it where it belongs. Write it as y equals 2 over x, and then write it as y equals 2 over x, and so on. The graph of y equals 1 over x is shown below. Use transformations to accurately sketch the graph of y equals 2 over x minus 4 minus 3. Complete the following for the rational function, the equation of vertical asymptote, etc., etc. All right, so they give us a few points. And there's a few kind of pointers as to how we want to graph this. And actually, we're going to start with there is no vertex, right? But there is something magical about 0, 0. So what's magical about 0, 0? Let's just go back a page. What's happening at 0, 0? The asymptote lines cross. If I stretch, you can sort of think of the asymptote lines as part of it. They're not, but you can think of it as they're part of it. So if I stretch, the asymptote lines won't go anywhere. If I reflect, the asymptote lines won't go anywhere. What's going to move this little crossing point here? The translations. So we know we've got 2 translations, right? We know that we have to go right 4, down 3. What's that going to do with our asymptote lines? It's going to move them so they go right 4, down 3. So the asymptote lines are going to cross here. So let's do that in green. So the asymptote line that runs along here is moved down 3. And the asymptote line that runs along here, and by here I mean which axis is that? The y-axis, is going to move right 4. So there's my new asymptote lines. Okay, and now we have to deal with, okay, so what else is going on? What else is going on? You can see it, it's on your sheet. There's a vertical stretch by a factor of 2. Okay, so where's this point? You go over 1 from the asymptote crossing point, right? You go over 1, up 1. So from the asymptote crossing point, I'm going to go over 1 and up 2. So this point is going to translate to, have been stretched to be up 2. This point here is a half and 2, so now it's a half and 1, 2, 3, 4. Okay, so again, it's vertically stretched. This point was 2 over and a half, so if I go 2 over, then I'm going to go where? 1. And I've got my 3 points. And I've got my asymptote lines good enough, right? I can sketch that. So I'm going to sketch that. So I know from here, it's just going to climb up there, and from here, it's going to fall down and end up there. And then we do the same thing on the other side, right? So again, this was 1 left, 1 down, so I'm going to go 1 left, but 2 down. This was 2 left and down a half, I'm going to go 2 left and down 1. And this was a half left and down 2, so I'm going to go a half left and down 4. I've got those 3 points now, and I can sketch. Not well, but I can sketch. So when we do rationals, I don't have a vertex, but I do have that sort of point, right? I do have the crossing of the asymptote lines, and they will still remain a horizontal and vertical line, and they are unaffected by stretches or reflections, but they are affected by translations. Okay, so all I have to do is look at the translations. If I have those down, and then just move my asymptote. So it's not the vertex, but 0, 0 is going to move to, in this case, 4, -3. Yep.
Wouldn't that point be on 7? It's 4 down.
Probably.
It's on 3, so 4 down from 3 would be 7. On that point.
Yes, it would. That's why it's sketched awkwardly.
Yes. Yeah. Right. Yeah. That's what I'm saying.
What you say is correct. It's good. It wasn't my bad sketching. It's because I put the point in the wrong place, and then the sketch went bad. So try and identify those points, right? So if you're drawing a sketch, at least anybody looking at it, we can see those 3 points, right? It's like we gave you 3 points, and now you can see 3 points. And remember, you should only work with points you're given, not points you assume are on the curve, right? Unless you have some other reason to think that those points really do belong there. Bring a magnifying glass with you next time so you go, oh, it's not at 4. Okay, what's the equation of the vertical asymptote? X equals 4 now, right? Because we moved right 4. What's the equation of the horizontal asymptote? Y equals -3, right? What's the new domain? No, so the asymptote is, and the domain is not, right? The asymptote is x equals 4. The domain is x cannot equal 4. And what's the range? Kind of the same deal, right? The asymptote is y is equal to -3, so the domain, or sorry, the range is that y cannot equal -3. It's all right. The graph of a rational function is shown. Draw the vertical asymptote. It should be vertical. Oh, draw the vertical and horizontal asymptotes. Read the whole sentence properly. And state their equations. Okay, so where's the vertical asymptote? Looks like -4, right? That's what they're kind of approaching. I'm going to shrink this a smidge. I don't know, 150? That'll work. Okay, so we got a vertical asymptote here, and where's the horizontal? What's with the 4s and the 3s? Just gonna walk out of here thinking it's always a 4 and a 3, right? I know there's a 4 and a 3. Unless you do the practice quiz, and then you'll say, I've seen that type of question. What's the equation of the vertical asymptote? So we have x equals -4 and y equals 3. What has that just told us? The translations, right? Left 4, up 3. Got translations. Okay, what is beneath this thing? The graph of the rational function is shown, stretched about the, I don't know, stretches, reflected, I don't know that, write the equation and the... So, instead of trying to describe it, first, it might be easier if we build up the equation first, and then we describe the transformations from the equation. Okay? So for rationals, I think it's easier. So let's kind of look at it and say, what are we aiming for here? So I'm aiming for an equation in this form, right? So we're going to do this, and then we'll go back and do this. So I'm aiming for an equation in the form y equals a over x minus h plus k, but I already know h and k, right? So we know h and k. Okay, so what am I going to write? Y equals a, don't know a, must find a somehow. Okay, x minus, or x what? X plus 4, left 4, right? And then up 3, so plus 3. Oh, okay. So I now have everything except for A. Now I need a point on the graph. If only there was an actual, and there is, right? Actually, there are two of them. So we've got negative 5, 6, or negative 3, 0. Pick. Negative 3, 0. Okay? Work out A. Okay, so you are going to substitute it in for x and y, either 6 equals a over negative 5, blah, 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 or what did we say? Negative 3, 0? No, we didn't say a was 0. No, we didn't say y was, okay. Get it right, y. Extend your page because if I hit that, I can lose it. No, that worked. 0 is equal to a over 1 plus 3. So I think a is negative 3. This whole reflection thing that they were talking about, it's done now, right? Okay, so what's the equation? And the equation is y is equal to negative 3 over x plus 4 plus 3. Show that. Yeah, okay. Now, we can go up and do B. The graph of the rational function shown is the graph of y equals 1 over x, stretched how? Vertically stretched. About the, apparently we're doing about the, again. By a factor of 3. Don't put, if anybody wrote negative 3, shame. Shame. The negative is not a stretch. You cannot stretch by negative, right? It's two things. There's a stretch and there's a reflection. So now we've handled the stretch. It's reflected in the x-axis. It is horizontally translated blank units to the blank. You got to go how many units first? 4 units to the, and vertically translated 3 units up. Okay? Doing this first, that would have been kind of, it's hard to look at that. What's the stretch? I don't know, like you should have gone 1 and 1, you've gone 1 and 3, you've gone down 3 instead of up 3, so that's reflection. You could have figured it out, I guess, right? Move over 1 unit, should be going down 3. Oh, I'm going up 3, so it's vertical by 3, and then it's reflected in the x-axis. But remember, the reflections happened before we did the trend. The final thing that happened was, right, everything happened in place here. This shape became this over here, and then it was moved. Right? So everything's happened. The stretches and the reflections are happening around the x and the y axes. These curves took place, but they took shape over here, and then they were translated. Okay? We look here and we say, oh, there's the translation. I see the translation. Right? That's the first thing we're going to see. And it's like, oh, I got points, so let me do this algebraically instead of, because you know, you should get it right, but Okay, any questions on that one? You can't vertically stretch above the y-axis. You have to vertically stretch over a horizontal line because you're moving up and down away from something. You can't move up and down away from a line that runs up and down. It's like there's nowhere to go. Oh, here we go. In summary, so the graph of y equals a over x minus h plus k is the graph of y equals 1 over x, blank stretched about the blank by a factor of, so what is it? Well, we've got to fill this in. Vertically stretched about the x-axis by a factor of, reflected in the x-axis if a is negative, which we say by saying a is less than 0. Or we could say non-positive. No, don't. Horizontally translated h units and vertically translated k units. Okay, and we'll deal with h and k's whether they're plus or minus. It's like, God, we've done that a million times now, right? I mean, nobody's looking at x minus 4 and thinking left 4. You are, however, looking at negative x minus 4 and thinking right 4 when you should be thinking left 4. But that's for another day. The mapping of the transformation is x. Okay, so what's going on horizontally? So really we're just going to say x plus h, right? We've got no horizontal stretch, and maybe there's a horizontal reflection, but unless it's in there, we don't know. So the a takes care of that. Okay, so x plus h, and ay, so we're doing the vertical stretch, and if a is negative, there's reflection, so ay plus k. The graph of y equals a over x minus h plus k has a vertical asymptote at x equals vertical, so it's an x equal. What does x equal? I'm going with h because the x and the h, they kind of go together. It's like, what makes this 0 if x is equal to h? So there will be a vertical asymptote if x is equal to h, and a horizontal asymptote at y is equal to k. Remember, they were at x equals 0, y equals 0, and what affected those lines? The only thing that was the translation. Not the stretch, not the reflection, just the translation. That's why your first step is, oh, here it is, draw the asymptote. What are h and k? Hey, look, I've got 1, 2 out of 3 things, and I've got an x and a y. There's only one thing to figure out. That's a. I learned my lesson from the last quiz. I will always write equations with an a value, and then I will plug in a point to figure that out. For the rational, wow, that's not in the right form, is it? The rational function, 3x, well, okay, we could do x and y-intercepts, right? I mean, that's just algebra. So let's do that. Algebraically determine the x and y. So the x-intercept, what do? You set y equals 0. So this becomes 0 is equal to 3x plus 1 over x plus 1. You keep in mind that x cannot be negative 1, just in case you solve this and get x is negative 1. It can't be that. You multiply both sides by x plus 1, ending up with 0 is equal to 3x plus 1. So what's x? Negative 1/3. Right? Which is cool, because that's allowed, right? X can't be negative 1. Anytime you're looking at a rational, just start thinking, maybe even right up here, just say, x, you cannot be negative 1. Yes?
Where did the x plus 1 go?
I multiplied both sides by x plus 1. What's 0 times really anything? 0. So as long as x isn't negative 1, you could do that. Okay, figure out the y-intercept, which I'm sure is much more difficult. It involves quadratic formulas and irrational numbers, and or it just factors nicely, or who knows. What's the y-intercept? What do we do? X. Oh gosh, well, is that any easier? What's y? Let's see, 3 times. Where's the quadratic formula? How come there's no? Shouldn't I factor this? Nope. Dude, that was pretty easy, right? So y is 1. Use division. Division? Seriously? I thought we were done with that. To express the equation, oh, you mean if we divide this by x plus 1, we'll actually end up with something that looks like this? I find that hard to believe. But let's give it a shot. So what have I got? 3x plus 1 divided by x plus 1. X plus 1. 3x plus 1. I'm going to use real division, none of that synthetic stuff. 3x plus 3. 1 minus 3 is negative 2. So then we would say what? Y is equal to 3 plus negative 2 over x plus 1. Right. Remember the analog, the just long division stuff? If we did 48 divided by 7, it would be like 6 plus, and then I shouldn't use 6 because that would be so. If we did like 47 divided by 7. 7 into 47 goes how many times? 6, and it's 42, 5. So that 47 is equal to 6 plus 5/7. Okay, so that's what we've written, right? Our y is the 3x plus 1 over x plus 1, and that's equal to 3 plus negative 2 over x plus 1. Now, putting it into this form becomes y is equal to negative 2 over x plus 1 plus 3. So now we know what that is, right? Or we know what happened, which we don't know just by looking at 3x plus 1 over x plus 1. But when you divide it, you've got this. So the equation of the vertical asymptote is, what makes this 0? X equals negative 1. The equation of the horizontal asymptote is, y, we just moved it up 3, right? So y equals 3. Accurately sketch the graph on the grid shown. Thankfully they gave us the 3 points so we can make a 3-pointer. We'll shoot from outside the circle. So, what do we want? Vertical asymptote. So let's sketch in our asymptotes. Hang on, I'm just going to shrink it a bit more. What was I at? So let's go to 125. Okay, so what have we got? Vertical, where? Negative 1 and y equals 3. And 3. Okay, and what's the negative 2 doing now? What kind of stretch? By a factor of, followed by a reflection in the x-axis. Okay, now, remember, this thing took shape in its exact position that it was. I'm just going to pretend that it's here, right? So, using red, we say if from the crossing point I go over 1, up 1, but I'm vertically stretched by a factor of 2, so now I'm up 2, but I'm reflected, so I am now, instead of 2 above, I am 2 below. Okay, does that make sense? Yeah. Doing that 1 point, right? So we take a point which lies 1 unit to the right of and above it's not the vertex, right, but it's the crossing point of the asymptote. So this function has a point that lies here. I vertically stretch it by a factor of 2 and then reflect it about, and this is now my line of reflection here. So this point here is 2 to the right and a half, so we go 2 to the right and a half. Vertically stretch it by a factor of 2 and then reflect it. So it'll be there. You could also do a mapping on this as well, right? So you could just say the point x, y maps to, give the new coordinates, throw in the point 1, 1, do the mapping, and get you'll actually get this point. Okay, you throw in the point 2 comma half, you'll get this point. And then where's this guy? It's a half to the right and 2 up. So half to the right and 2 up. We'll go 4 up. Now it's 4 above, so we got to go 4 below. Okay, and then we're going to sketch this and this. So you do the left side. Same deal, right? So I just say, okay, got a point, it's here. So now it's here. Now it's here. And I got a point that's a half and 2, so half and down 2, so it goes down 4. So it's going to be 1, 2. Add 4, 7. And I got a point which is 2 to the left and a half down, so 1, 2 and a half down. 1 down, but 1 up. If you want, do it in 2 steps. Like just do the black one. You know, get these lines, which will now look like this and this, but this will be centered here, and then move the whole thing over 4 and up. Right? Or do the mapping. Does it ask us to do the mapping? I don't think it does, right? So you could do the XY maps. Do you want to do the mapping and then just check it on a point? Just say, oh, look, that works too. So it's, okay, do the mapping. Figure it out. Okay, but you actually have to do the mapping. You don't just say, yeah, let's do the mapping. Actually, you didn't. But do the mapping. Good practice. What's going on? Is that the mapping? Okay. So where's the point 1, 1 go? Like 0, 1? Where's the point 2, 1 half go? So 1, that's a half, so negative 1 plus 3, 1, 2. 2. Where's the point a half 2 go? Negative a half, negative 4 plus 3, negative 1, negative a half, negative 1. Right. So you could do that as well, right? You could do the mapping, take the point 1, 1, just figure out it goes there. Take this point, it goes there. Take this point, it goes there. That's how you sketch it. Do the same thing for these guys. You have seen that the vertical asymptotes occur at the blank of the rational functions. Which blank? We're going to go with the non-permissible. I wouldn't have guessed it either. I had to look. It's the non-permissible. It's like a big blank, though, right? The non-permissible values. I'm always looking at restrictions more than non-permissible values, right? But use this concept to algebraically determine the equations of the vertical asymptotes of each of the following functions. Okay, well, the first one's pretty easy. So what's the first one? So all you can do is this. The non-permissible value would be if 3x plus 1 were equal to 0, which means that 3x would be equal to, and x would be equal to And, okay, same deal. The non-permissible value will occur if this is equal to 0. Boil it up. There are a number of you who factor things and do not check them, or you check them faultily. If you know, and at this point you know if you are a person who factors and gets it wrong, take steps to avoid that. Okay, so I don't know if you're factoring it, you're foiling it out, and you're just getting it wrong. In which case, figure out how to foil it out better. Because if this goes wrong, stuff goes horribly bad, right? I mean, you could lose half a mark. It's like you factor, okay, it's a half mark off. But you could also turn something that's relatively easy into something that's, 10 minutes later, I'm just wrapped up in this big mess. Okay. So in this case, there are two vertical asymptotes, right? Two vertical asymptotes. And then, seriously? Okay, 8. 4 and 2, 21, 7 and 3. Okay, put together 4, 2, 7, 3, get a 22. Minus 7 plus 3. That actually works. Amazing. And again, so two vertical asymptote. They now become VAs, not to be confused with VSs. Two vertical asymptotes again. So if you graph this, you will see two vertical asymptotes, right? If you graph this, you will see two vertical asymptotes. The horizontal asymptote of a rational function can be found by determining the limit of the y-coordinate as x tends to infinity. Or absolute value of x. So if x gets really large, so if x is 1 million, what are you going to have? 7 million minus 8 over 3 million plus 1. Okay, the minus 8 and plus 1 really don't enter into it at that point, right? So it's really just 7 over 3. Okay, so if your x value gets large enough, your y value is just going to become 7 over 3, right? Minus 8 and plus 1 don't do much when it's 7 billion and 3 billion, right? 7 billion over 3, or sorry, 6,999,998,992 over 3,000,000,001 is 7/3. Okay, so you just go y equals 7/3. In the second instance, again, we think if x is 1 billion, is the 5 going to do anything? Nope. If you square 1 billion, is subtracting 2 billion from it really going to change its value that much? No, not really. Right, they won't have much of a contributing factor. So we're really left with like 2x over x squared, which is really 2 over x. And if x is getting really large, what's 2 divided by a really large number? What's 2 over 1 billion? 0, pretty much. So this will be 0. So the first one, you have powers of x that are the same, so really it just becomes the numerical coefficient, 7 over 3. The second one, the 5 doesn't contribute much to the 2x, and the minus 2x plus 3 doesn't contribute much to the x squared. It won't change its value. So you really have 2x over x squared, but that simplifies to 2 over x. And as x gets really large, 2 over x tends to 0. It's not 0, but we're looking for the asymptote line, and that is 0. Here, you're really just looking at these. Like, that doesn't have any contribution, so it's 3x squared over 2x squared, which is 3 over 2. Okay. And if you don't believe me, throw a billion in for x and work that out and work that out. Right? Like, a billion squared is, what's a billion squared? It's like 10 to the 8, 3 times 10 to the 18th minus 10 to the 9th. It's like, yeah, that's so far out there and all the zeros, it's not significant. And this guy, that's going to be really, really big, and these guys don't even really enter into it, right? So what's going to happen there? The 2x squared is going to get so big that the 5x plus 4 can't really do anything to it, right? So there is no asymptote there. It's just that number's just going to keep increasing, okay? So you won't have a vertical asymptote. You think, I'm going to end up with 2x squared over 5. So if you follow the same sort of logic, you say I get 2x squared over 5x, which is 2x, and if x is getting really large, then this is just really large. It's just infinity, right? So there is no horizontal asymptote. There's no line that will approach. So we could just say, this would, 2x over 5. 2x over 5. So as x approaches infinity, so does 2x over 5. Okay, so no horizontal asymptote. Welcome to Unit 1 of Math 31. You get to do limits and stuff. For each function below, describe the transformation that was made to the graph of y equals 1 over x squared. So now we're doing 1 over x squared. And use the transformations to accurately sketch the function on the grid shown that contains the graph of y equals 1 over x squared. All right, so we should now be able to look at this and say what's going on. What's going on? Number 1. So a vertical stretch by a factor of 2 about the x-axis. We'll just throw it in occasionally. What else? Vertical translation up 1, so that's number 3. What else? Horizontal translation left 3, right? X was replaced by x plus 3. The horizontal translation left 3. Okay, what are we supposed to do with this? Sketch it? All right. So, what's the first thing we're going to sketch? Our asymptote lines. Okay. Where did our asymptote lines go? They went 3 to the left. And they went up 1. And it's vertically stretched by a factor of 2. So you could just stretch it in place and then move it 3 left and up 1 if you want, right? You do that. So this is 1, 1, stretch, and then go 1, 2, 3, up 1. Or you could say the point that was here, 1 right and 1 gets there. And I've already moved it left 3 up 1. So. And this guy here gets what? Vertically stretched by a factor of 2, and then goes 1, 2, 3. Oh, no, wait, sorry, it's here. 1, 2, 3, 1. And vertical stretch. I mean, that's going to climb faster, but it's like whatever. So just. Okay, don't get too fancy. So show that one point, right? Show that one point. Give us all something to work with. How we doing? Oh, lots of time. You could do a mapping as well, but I'm not going to. For each function below, describe the transformation was made to the graph y equals 1 over x squared, and use the transformations to accurately sketch function of grid shown. That contains the graph y equals 1 over x squared. Okay, what's x squared minus 10x plus 25? X minus 5 quantity squared. So, describe the transformations. What's going on? Number one, there was a vertical stretch by a factor of 3 above the x-axis. But that's not a 3, it's a negative 3. Or there's a negative, so what's the negative do? It's a reflection about the x-axis. Followed by a horizontal translation, HT, right 5. Oh, sorry. The description goes down there. All right, so I think what I would do is just do it in this order, because you're only really working with that one point, but then keep in mind, hey, it was reflected, so. All right, what have we got? Vertical by 3, reflection, and then right 5. Vertical by 3, reflection. Vertical by 3, reflection. Now, right 5 means that was there any up or down? No, so where's my asymptote line is still here then, right? So although this point here, which is almost at 0, is stretched by a factor of 3, so that it's 3 times of almost 0. So really, these guys just kind of flip underneath here. They're just going to tuck in on the other side here. And I've got this here. It's reflected, so it's opening down. Okay, so I'm really looking at that goes down, and that comes to there. And that goes down, and that comes to there. And you could kind of do it the same way. You could say, I'm going to do my stretches off of this here. Yeah, it doesn't make as much sense in this case as it does in the other case, right? Because you're not dealing with 3 points. You're dealing with 1 point. It's just... All right. Is that all there was? What else is there? Oh, this looks important. Because it's kind of big. Wait, let me... And this isn't even view full size. Hang on. View, zoom, page width. See? Look. So, apparently you should read page 439, example 5. It says on here, make sure you go through this example carefully as there is nothing like it on the worksheet. Okay, so go through carefully.